Purpose of our redox titration is to determine the concentration of an iron ion solution. The reactants in our redox reaction are going to be sulfuric acid, potassium permanganate, and iron sulfate. The iron sulfate is actually already mixed with the sulfuric acid. The mixture forms a relatively colorless solution. Potassium permanganate, you will notice, forms a very dark purple solution. Let's take a look at the redox reaction that will occur. Well, iron and manganese are going to be the substances that are oxidized and reduced, so I'm going to save a little bit of time and only assign oxidation numbers to iron and manganese. Iron sulfate on the reactant side, that iron would have a +2 oxidation state. The manganese on the reactant side has a +7 oxidation state. On the product side, the iron has a +3 oxidation state and the manganese has a +2 oxidation state. So we can now determine the substances that are oxidized and reduced. We can see that manganese goes from a +7 to a +2. We can also see that iron goes from +2 to +3. Now we have to be careful here. There are 2 irons on the product side, so we need to balance that immediately on the reactant side by putting a 2 in front of iron sulfate on the reactant side. We can see that manganese goes from a +7 to a +2, which means it's gained 5 electrons. It has been reduced. The iron will be oxidized. In this case, it's going to lose 2 electrons. Now, it appears as if it only loses 1 electron, but remember, we have 2 irons, each losing an electron, so it's a total of 2 electrons lost. So to equalize the number of electrons, we have to multiply the reduction reaction by 2 and the oxidation reaction by 5. Those numbers that we are multiplying by then become the coefficients in front of those substances. So we can put a 2 in front of KMnO4 and a 2 in front of MnSO4. We already have a 2 in front of iron sulfate. When we incorporate the 5, we're actually going to multiply by 5, so that'll become a 10. And we'll put a 5 in front of the iron 3 sulfate on the product side. These coefficients on the product side are not going to change. The rest of this can be balanced by inspection. We will need 1 K2SO4 because we have 2 potassiums over here and we have 2 potassiums right there. We will need 8 H2SO4s and we will need 8 water molecules as well. So that is the balanced redox reaction that will occur as we titrate. The chemical being oxidized, in this case, is FeSO4. The substance or chemical that is being reduced is actually KMnO4, but it also has to include the acidic solution. So we're going to include the acid in there as well. If we don't have an acidic solution, this is not the reaction that occurs. So the substance that is reduced is going to be KMnO4 and H2SO4. The oxidizing agent, remember, is the substance that is being reduced. So that's the KMnO4 sulfuric acid. The reducing agent is the substance that's being oxidized, which is the FeSO4. The purpose of the titration is to determine the concentration or standardize a solution of FeSO4. We're going to use the balanced equation that we just came up with to help us determine the concentration. We are going to know the concentration of the KMnO4. In the practice titration, it will be 0.020 molar. We are trying to determine the concentration of iron sulfate, so we do not know the molarity of the iron sulfate. When we perform this titration to the endpoint, we will have data that we can use to determine the concentration or the molarity of FeSO4. We are going to start by using the volume of KMnO4 that were required to reach the endpoint. We'll take this number, which we don't know yet. We'll be able to get 4 sig figs for that number, but we're going to take the volume of KMnO4 we used and we're going to convert it to moles of KMnO4 using the concentration. So we know 1 liter of KMnO4 will be 0.020 moles of KMnO4. Well, I don't want moles of KMnO4, I want moles per liter of FeSO4. So to convert from moles of KMnO4 to moles of FeSO4, we will need a mole ratio from the balanced equation. So the mole ratio between FeSO4 and KMnO4 is 10 to 2. 2 moles of KMNO4 is 10 moles of FeSO4. So we're almost home. We are now in moles of FeSO4. We want moles per liter. The last thing we need to do is divide by the volume of FeSO4 that were used in the titration. Make sure you convert it to liters. So when you think you've reached the appropriate endpoint, you just simply need to do the calculation and check to see if you are in the practice titration range. What does the endpoint look like? Well, let me explain that a little bit. The KMNO4 is purple. As it reacts with the iron sulfate, the color goes away. You'll actually see iron 3 ions form, which form a little bit of a yellowish color. But as soon as there is no iron sulfate left to react with, then the KMNO4 color will not change. It will not change to colorless when it reacts. So it'll stay that purple color, but in a very, very dilute concentration. So it won't look purple, it'll look a salmon color. So we are actually going to titrate to a salmon endpoint. So when you start the titration, it's going to be a relatively colorless solution. As you add KMNO4, you'll see a yellow tint because of the iron 3+ ions. We want a peach or melon or salmon colored endpoint. If you go past, you will get a very bright pink color, which we do not want. Here are actual pictures of the cup at the beginning of the titration as we're titrating to get that yellow color with the appropriate endpoint. And here is the pink color that you will get if you are way past the endpoint. Now it's time for you to go practice your titration. When you think you have the right color, perform the calculations and check to see if you are in the appropriate range.